Today's lesson will be about gravitational fields. If you go to Wednesday, April 22nd, you'll see a version of these notes for you to print off or just download so you can read if you want to do that. And a couple of videos to also walk you through some explanations and some problems, some different problems to look at gravitational fields. So you can do that if you'd like. Otherwise, fields. I highly recommend, and I'll put this link down in the description for you to watch. American Scientific does a really good job explaining what fields are, so I'm not going to dive into it like they do. I'll just give you a basic definition. So please watch this video. It's pretty short. Otherwise, just so you would know, if you're not going to watch it, a field is a physical quantity represented by a number or a tensor that has a value for each point in space and time. Now, a tensor is you can just view that as a collection of numbers or vectors if you want. That's all a tensor really is, so it's a fancy word you can add to your new collection of words. So when I think of fields in the simplest terms, I think of a temperature map. So here's a map of Canada. These temperatures are in Fahrenheit because that's just where I stole it from the internet. It was off an American site. So it gives you a rough idea. A number has been assigned to a location, and that number gives you some information of what the conditions are like in that location. So for instance, Vancouver is 43 degrees Fahrenheit. So that's just a little bit above freezing. And so that gives you a rough idea of what that temperature or what the weather conditions are like. So for instance, Saskatoon is at 11, so that's below freezing according to the Fahrenheit scale. It's actually pretty cold. Calgary is slightly warm, not as warm as Vancouver, but it gives you a rough idea of what the average kinetic energy of the air molecules are like in that area. And that's really all a vector is about. It gives you a rough idea of a certain quantity. In this case, it's temperature. Now, temperature is a scalar quantity. This could be a vector. So I could give you a map that has all the wind velocities. So I could have a map that shows maybe there's a wind with a speed of, I don't know, 30 kilometers an hour near Saskatoon going to the east. So as soon as I give it a number and, of course, a direction of the wind, I now have a vector. And then slightly north of Saskatoon, maybe it's going northeast. Right. So if I go to Lloydminster, maybe it's going southeast. So it could just be in lots of variation as you go across Canada or even down to the States. So that's an example of a wind velocity field, if you want to think of it that way. So think of it kind of like a map. So you have a bunch of numbers assigned values for every single location on this map. And that's really all a field is. So a field, in this case, when we're talking about gravitational fields, which is what today's lesson is going to focus on, think of it as that temperature map, but each of those numbers are actually a value of force. Because in a gravitational field, when you have masses in a certain region in space, they're going to create a force of attraction for different reasons. There's Newton's reason, I'll explain that shortly, and then there's Einstein's reasons, which is what we accept as valid today. So in the next little while, next few lessons are going to be about gravitational fields. So next tomorrow's lesson, and by tomorrow I mean the next video I record, is going to be about how that affects orbital motion. And then I'll make 2 videos, maybe 3 on about electric fields, and then maybe 1 or 2 on magnetic fields. All of these things, these gravitational fields, electric fields, and magnetic fields, they basically are the same in principle. And so that's why they're grouped together in their own little unit. Electric fields, this is big capital letter E. Actually, it's capital letter epsilon, which is the same shape as big capital letter E. I was taught to use lowercase epsilon for the electric field strength, but I'll maybe explain that when we get into that unit. Nowadays, more people I notice are in textbooks are going with capital E, but to me, this is confusing because energy uses capital E, and I don't want to make this more confusing than it needs to be. So today is about gravitational fields, but first, a little bit of history, and just because I like Simpsons, here's Milhouse doing his little science experiment about gravity. It's terrible. Anyways, way back in the 1600s when Newton was quarantined away due to the plague that was in Europe, the big black plague, he kind of was staring at the skies and the cosmos, and he was trying to figure out why the planets are the way they are, why they keep moving the way they're moving, and he invented calculus to help back up his claims. And by observing Jupiter's moons, he was able to kind of figure out that they move the way they move because there's some sort of proportionality to their masses. Right? So there must be a force of attraction, and that force of attraction must be caused by their masses. The more massive something is, the more it is going to have some kind of a force of attraction. So because there's some kind of proportionality involved, you can think of it in terms mathematically as, well, if you double one of the masses, your force is going to double as well. So we use the symbol for proportionality, this little alpha symbol, if you will. So it just means they're not equal, right? So if, let's just suppose this mass was 2 kilograms and this mass was 4 kilograms, we're not going to get a force of 8 newtons. But there is a direct relation where if you double one of these masses, you will double the strength of the force involved. If you cut one of these masses in half, you will cut the strength of the force in half. And that's all the proportionality is getting at. So the strength of the force has something to do with the masses involved. Also determined that as you move further away, the strength of the force decreases exponentially. And so therefore they have an inverse square relationship. Right? If you decrease the force, so if you bring two masses closer together, the force is going to increase exponentially. And so again, this is called the inverse square law. So there is inverse square proportionality involved. So the force of attraction between two masses, according to Newton, were based on the two masses involved and how far apart they were separated. So that means they're proportional to all these things at once. And that's kind of where Newton got his start. Right? And so in the world of physics, when we find a direct relationship and we go, okay, well, there must be more involved. And so often what happens in physics and a lot of math is we change this from a proportionality scenario and we turn it into an equation where we label a constant k. So the constant k is a placeholder because, well, there's something involved here that is not making these equal. So we're missing something. And if you want to figure out what that constant proportionality is, it's just a matter of doing some manipulation, bring the denominator up, bring the numerator down, and then you solve for that unknown constant. Now, at the time, we didn't really know or understand what that constant is. All right, mass 1, mass 2, drawn with a mouse, kind of ugly. All right, and so they just solve for that, and later we find out that this has a lot of weight to it, in the sense that it got its own symbol later on. So this is known as the universal gravitational constant. So when you manipulate the equation, like I showed in that last slide, you end up solving for it with some gravitational observation values, obviously. So they've been monitoring for a while and they knew what the masses of certain planets were. I won't get into how they know that. That's a different topic for a different day. And they knew the distance separation. They could actually measure forces by observation. And they were able to determine the value should be 6.67 times 10 to the negative 11. And when it comes to the units are awful, right? Newton meter square per kilogram square. The units for a constant are typically ugly because they're trying to make, basically, a force should be a Newton in the end. And so this constant should have the units to cancel out everything else that is being multiplied and divided by. So that's why the units are as ugly as they are. So it took about 100 years before the famous Cavendish experiment was able to actually determine experimentally what the value of G was. And so that was good, and there was a lot of rejoice in the astronomical and scientific community. But the main thing is we now have an equation that explains why the planets are orbiting around the sun, why there is this attraction between masses. And this is what Newton came up with, right? This whole notion of, well, if gravity exists, just be based on mass itself. For whatever reason, mass attracts mass. And that's pretty much what we got. And this equation is still valid to today because it was based on observational data. What's going on out in nature right now? So he came up with this equation to explain what's going on in nature. The theory behind it is still, well, it's accepted, just not Newton's version, because that's the fun thing about scientific theories. They can be amended as new evidence comes up. So, but for right now, this is the 1600s, mass attracts mass, and that was good enough. So even Newton didn't really think that that was good enough for him. And so to paraphrase, he basically said that he's leaving up to other people to figure out what's actually happening. So there's his famous quote if you want to read it. He doesn't really think mass actually attracts mass, but that's what he was able to come up with. Sooner or later, someone will come up with a better explanation. And that's essentially where he left it back in the 1600s. Flash forward to the early-ish 1900s, and Einstein came around, and in 1905, he published a handful of papers. One of them was special theory relativity. Special theory relativity kind of related some weird quirks that he came up with light, and then he determined that that wasn't good enough because special theory relativity was dealing with non-accelerated states, so only states that were in an inertia. So therefore, he had to think harder and figured out that, well, what if you have things that are accelerating? And so after about a decade, almost a decade after he published his papers about special relativity, he came up with general relativity, which was supposed to explain everything in the cosmos. And so he came up with this whole notion that space and time are one and the same. And it's not that mass attracts mass, it's that mass can actually warp space and time. So if you can think of it as a trampoline, here's a light beam going through space, you know, if you want to imagine the sun there and Earth there, as light travels from point A to point B on this map, it's going to travel in a straight line. If you get a large mass involved, that large mass is going to warp space and time and therefore bring light and warp light with it. And so you can view that as maybe you are sitting on a trampoline, you're going to warp the trampoline down into the third dimension. So the thought is that mass is warping space and time into the fourth dimension, if you want to visualize that. He also found out that not only does it warp space, but because it warps time, as you get closer to larger massed objects, time actually slows down. When you move further away from massive objects, time speeds up. So that's another quirk of his general theory of relativity. That's a topic for a different day, but if you can just remember that fact, then that should be enough to bend your head a little bit. So think about being on the trampoline. I'm assuming at some point you've been on a trampoline in your life. You can imagine having a larger friend, or think of when you were maybe young and maybe your dad or mom got on the trampoline with you. They're going to create a large wow in the trampoline, a little dip in the trampoline, much like a large mass is going to really warp space and time, whereas a small mass, it's still going to warp space and time. But if you, again, visualize yourself on the trampoline, odds are good when you had a large person on the trampoline and you were a small person, often you would just fall towards the person making the big dip. Now, of course, the way physics works, because you are also creating a dip in the trampoline, the big person will also fall towards you, but it's not going to be as obvious. They have a larger mass, so they have a much smaller acceleration. So more often than not, it's going to seem like only the small mass is doing the moving, but technically they will move towards each other. So that's one way of viewing that. Okay, large masses warp space and everything else falls towards it. So that's what's happening with the moon. But of course, the moon has tangential velocity, and so therefore it's just going to go around Earth as it's trying to fall towards Earth. So that's viewed as projectile motion, where Earth curves away, and therefore it's always in a state of falling towards Earth. But there's some nuance with that as well, which I won't get into in this video. So this is what it's like when you have two masses that are close together in a field. So this is your space, and both of these masses are warping that space. So that is their gravitational field, right? At all points in this little checkerboard here, you would have your gravitational field providing you with some kind of value, telling you how strong that gravity field is nearby. When you're really close to it, it'd have a large gravitational value. When you're far away, it has a weak gravitational value. Kind of like how if you're on Earth, you feel Earth's gravitational field pulling you down. Well, maybe you don't feel it, but there's Earth's gravitational field pulling you down at a rate of 9.81 newtons per kilogram, or 9.81 meters per second squared, because you can view it as an acceleration of gravity. As you go further up into the atmosphere and leave planet Earth, that value gets weaker and weaker and weaker and weaker as you go further away from Earth, because you will not experience Earth's gravitational field anymore. So yeah, it's kind of like also, if you think of flowers in the spring, When you're nearby them, you can smell them, but if you go across the lawn, you can't smell them because they're too far away. You have to be somewhat close to really experience it. So the more massive an object is, the more warping of the space and time. So the sun is our big star in our solar system, and therefore it's providing all of our planets in our solar system enough gravity to stay near the sun. Likewise, black holes do the same thing. In fact, there's massive black holes at the center of our Milky Way galaxy, and it's basically behaving like the sun, keeping all of the planets and stars in our Milky Way galaxy. So this warping is seen as the gravity field. So how you actually determine the gravitational field strength. So let's actually be simple about this. Let's combine Newton's second law, where the net force is equal to the total forces acting on a mass, which is equal to the mass times the acceleration. So this is just any mass. If we're going to just be simple about it, let's just say we're talking about you on planet Earth and you experience Earth's gravitational field. So let's just say that little m is you. Newton's law of gravitation says that if you're standing on planet Earth, your mass is attracted to Earth's mass, and therefore there's going to be a force of attraction between you two. So if you combine Newton's law of gravitation with Newton's second law, you would actually have this. So this is the only force involved, Newton's law of gravitation. You're standing on the surface of Earth, and so therefore that should be equal to your mass times the acceleration that you would experience. So if you cancel off your mass, because your mass is not important at this point because it's on both sides of the equation, you'd end up with your gravitational constant multiplied by the mass of Earth. I made the mass of Earth a capital M just to kind of really point out that that's a much bigger mass, and therefore it's going to be the one that's going to create a gravitational field. Well, divided by the distance squared between the center of you and the center of Earth. So this squared distance is always from center of mass to center of mass. And if you're standing on the surface of Earth, well, then that's just the value that you've been using in all of your kinematics equations when you're talking about dropping objects. So that's just going to be 9.81 newtons per kilogram or meters per second square, however you want to view it. And that would be your acceleration of gravity on Earth. If you go higher up in the atmosphere, you'd have to add on that distance to this value here. And when this number gets larger, the value for gravity gets weaker. So it's all determined how close you are to the center of Earth. So for instance, here's you're on the surface of Earth. You have about a 1 meter distance from the ground to your belly button, your navel, which you can pretty much ignore. So if you look at scientific notation, that's 1 times 10 to the 0, which is pretty meaningless. If you consider the radius of Earth to be 6.38 times 10 to the 6 meters, so that's the distance to the center of Earth at the equator. It's shorter if you're at one of the poles, but let's just, again, be simple about it. Let's use one number. You're in the millions if we're going to the center of Earth for meters, right? Thousands if we convert this in kilometers, but let's just keep it in meters. Compared to you, your distance to your center of your mass is pretty meaningless with respect to Earth's radius. So very often when it comes to dropping objects off buildings, off cliffs and whatnot, we can still get away with just saying G is equal to 9.81, and we don't actually go through the trouble of solving for a different value of G, because you've got to be pretty high up in the atmosphere before you'll even change it to 9.71, before you can change it by 0.1 of a meter per second square. So usually you got to be somewhere between 10 and 20 kilometers up in the air before it's going to actually make a difference. So by and large, we usually just stick with 9.81 on the surface of Earth. Near Earth's surface is usually the good judgment to call it 9.81. So if you're just going to talk about the gravity on a planet, you can change that value of D to just R and say it's the radius of the planet. If you're above the surface, you'd have to add on the altitude, and then very often it would just turn into D is equal to your radius plus whatever your altitude is, your height. If you're given an altitude, you just have to add that in to figure out what your gravitational field strength would be. So again, by average, if you actually plug in all the numbers, you get roughly 9.8 newtons per kilogram. So this gravitational field strength is actually hidden inside Newton's law of gravitation. So this is the gravity field that we're talking about. So this is that region in space that pretty much dictates what that force of attraction would be. You just need to know what the mass is in that gravitational field, and then you can actually find out the weight. So it's hidden in this equation. you can see it right there. You've got the gravitational constant multiplied by the mass of planet Earth, all divided by the distance squared between the center of Earth's mass and the center of your mass, or an object's mass on Earth. And so therefore, if you actually substitute that into Newton's law of gravitation, you actually get the equation for weight on Earth. And so that is the simple version of the weight equation. Otherwise, you're always actually just doing Newton's law of gravitation if you're trying to find the weight. You just happen to know that you're on the surface of the planet. When you move up out of space, you'd probably need to just go back and use that equation for Newton's law of gravitation, right? Because you'd have to figure out what the actual distance is between the two center of masses. So I've got a couple of problems. I'll try to go through them fairly quickly with you guys. Calculate the gravitational force between two objects that are 0.75 meters apart. Each object has a mass of 50 kilograms. So this is just kind of getting used to the equation. So recognize that you're just doing a force of gravitational attraction. Therefore, you just plug in the numbers. There's a lot of plugging and playing in this unit. You'll have this number memorized shortly, 6.67 times 10 to the negative 11 Newton meter square per kilogram square. Yes, those units are ugly, but you'll get used to it. If you have two masses that are identical, I could have just said 50 kilograms squared, but I don't want people to think that you always square that value. And it's just a matter of plugging stuff through. Cancel off the units, so kilogram cancels the square, kilogram cancels the other kilogram per kilogram, I mean. Likewise, if you square the denominator, so multiply the numerator through, you end up with that. If you square the denominator, you end up with 0.5625. I'm just keeping the numbers short and simple on here. The masses, sorry, the meters square should cancel out. Please make a note. I'm going to really point this out. When I have parentheses here, I have to square both the number and the unit. If there's no parentheses between the meter and the square, that means this is one unit, as a friendly reminder. I don't want to see anyone square this again. Okay, and when you do square this stuff, I expect to see these parentheses in when you write your numbers out the first time. So meter square cancel the meter square, and it's just a matter of plugging the numbers through. You're going to end up with a lot of scientific notation in this next little while, so you'll have to make sure you remember how to enter that into your calculator. So essentially, if you have two 50 kilogram masses that are almost a meter apart, so 3/4 of a meter apart, you'll have a force of attraction of approximately 3 times 10 to the negative 7 newtons. Now, this is a vector, but since the force of attraction is towards each other, I was not specific from the left one or the right one, or I could have drew these two odd masses above and below each other. It wasn't specified. So if it's not specified, then all you really have is the magnitude of the strength of the force. Okay. So as a reminder, this is our solar system. You probably saw this, a version of this a long time ago in different years of school. I think you should have seen us a little bit in grade 9, but that was grade 9. Asteroid belt, we more or less ignore. We have 8 planets and a handful of dwarf planets. Pluto got kicked out of the planet family mainly because when it was discovered in the 1960s, it was like, hey, there's a planet way out past Neptune. Isn't that cool? But its orbit actually crosses over Neptune's orbit. I think in the 2000s, early 2000s, Neptune was the furthest planet away, but that won't happen for like another 800 years or so. Don't quote me on that number. But since Pluto was the only one that they really knew about, aside from Ceres at that time, that was about that. It was really, really small, about the size, just a little bit bigger than our moon. We thought, oh, it must be a planet, but we keep finding other ones. So makes on here. It was Eris, when they discovered Eris just outside the Kuiper belt, that they kind of said, hey, we're finding more of these planets that are really small in comparison to the other ones. So we have to make a whole new category. And then they came up with the idea of calling them dwarf planets. That scientific community doesn't really care if they're dwarf planets or not, but the main public kind of got annoyed with that because they remembered 9 and they don't want to learn anything new. Anyways, this is our main solar system. You have a solar system chart on page 68. You're going to be using this a lot because a lot of the questions that you're going to see in the near future don't actually have numbers for you. So if you're told you're involving the sun and Mercury, you have to be able to look at this chart and understand where things are. So a quick little description of the chart. So the chart is about 40 years old. So some of these numbers are slightly out, but not by much. So for instance, I believe the accepted value for the mass of the sun is now 1.99 to 3 sig figs, just as an example. So I'm not too concerned. these numbers being slightly out, because I'm more concerned that you understand how to do the math involved and you understand the physics involved. So I'm a little bit lazy. I'm not going to fix all the answers on the answer key to, I don't know, make it better, I guess, because that takes a lot of new time to do that, and it wouldn't be changing the answers by much. So therefore, I'm just going to ignore it. And you're going to use old data, and you'll have to be used to it. So for instance, Pluto's on this chart, right? It shouldn't be on this chart anymore because these are the main planets. The chart could be infinitely large if you consider every planet, every rock that we've discovered out there. So this is what you have to work with. So masses are there in kilograms. You'll notice it's all scientific notation. The radius of the object, they vary in size, right? From an order of magnitude of million to 10 million to 100 million meters. So the sun is the largest thing in our solar system, and it's got a radius in the basically 700 million meters in size. The moon is in its own little category, and that's because the moon orbits Earth. All of these planets orbit the sun, so they're in their own little category because that's how they orbit. Period of rotation on axis, I don't think you'll actually use this. I don't think there's any questions that use this value. This is just a day on the planet, how long it takes for the planet to orbit itself, so just rotate upon its own axis. The mean radius of orbits, so you'll notice the sun doesn't have any values for those, and that's because we orbit around the sun. We go around the sun, therefore it doesn't have its own value. The sun orbits around the big set of black holes at the center of the Milky Way galaxy, but we don't care, not for our purposes. So this is how long it's going to take, or sorry, this is how far away each of these planets are from the center of the sun to the center of those planets. Now this is the mean radius, which means it's the average radius. The planets move in ellipses, so sometimes we're slightly closer to the sun, sometimes we're slightly further away, but we just have the average value. If you need to know more accurate information than that, then you're probably on your way of getting a astrophysics degree, and at that point you'll have that information available to you. If you're just doing basic grade 12 physics, this is good enough for you. Period of revolution of orbit, this is how long, this is a year. So if you kind of want to remember that, this is a year, how long it takes to go around the sun. Now the moon, again, this is how long it takes to go around the Earth. Right, so roughly every 28 days the moon goes around the Earth, so that's why this number is quite a bit smaller, but this is all in seconds, and this is roughly how long it takes for Earth to go around the sun. So 3.16 roughly times 10 to the 7 seconds. Kepler constant, I'll get to later. We'll talk about that in the next video. Anyway, so that's your chart. Sorry, you didn't need to cancel that out, but that's your chart on page 68 of the notes. Okay, so that chart's important because you'll have questions like this where there's absolutely no numbers. So for instance, calculate the acceleration due to gravity on Jupiter, or it could have worded this slightly different, calculate the gravitational field strength on Jupiter. So in that case, you're just looking for what the acceleration of gravity is on the surface of Jupiter, if you could actually stand on Jupiter. So the gravitational field would basically just be, you plug in the equation, gravitational constant multiplied by the mass of Jupiter divided by the radius of Jupiter squared, because you're on the surface. And so it's just plugging in the numbers. You have to recognize, and the hardest part, I've noticed when I mark some of your guys' stuff, at least students in past years, they will sometimes pick the wrong numbers. I once in a blue moon will pick the wrong numbers. So if you guys are working through your problems and you'll notice that, hey, you got the wrong answer, double check that you actually use the right numbers. It's not uncommon for someone to plug in the mass of Mars or the mass of Saturn just because your eyes play tricks on you and you think you're picking the right number. So just make sure your numbers are correct. Another thing that students find is that, again, by the time you're done plugging the numbers through, you get the wrong answer and you go, well, why is that wrong? Just double check your math and make sure you actually squared your denominator. So there's a lot of mathematical errors that can happen. So just make sure you understand how to work your calculator. Another thing that people find make a lot of mistakes on is when you have this chart given to you, sometimes you'll use the radius of the object and sometimes you use the main radius of orbit. So make a note on here. If you printed this off, you didn't print this off, it's fine. But do make a note that mean radius of orbit is the distance to the sun, right? Center of one planet to the center of this. That's what this has to be seen as. Radius of object, this is just for the planet itself. So plug in the numbers appropriately and then just do the math. If you square the denominator, you end up with that. Cancel off the units there. Only one of these kilograms gets canceled off. So we'll cancel off that square with this guy here because it's per kilogram square. And you should end up with a roughly 25 newtons per kilogram, 24.6 specifically if you use 3 sig figs. And for the most part, there's 3 sig figs everywhere on this chart, almost everywhere. So just stick with 3 typically for your final answers. And yeah, so its gravitational field on Jupiter's surface is it's not even 3 times that of Earth, but it is a gas giant, so there's not a lot of mass there. Yeah, so there's that. You get some questions that are a little bit harder, where it asks for what is the maximum force of attraction between Earth and Mars. So I have to remind you of where they are in the solar system. So if we're looking for the maximum force of attraction, we want to know when the 2 planets are closest together. So that is when the force would be the strongest, because the distance separation will be the smallest. We don't want to know what that force of attraction would be when Mars is, say, over here, because at that point, that is a much larger distance away. And if you increase this distance for your force of attraction, it's going to decrease your force exponentially. So, according to the solar system chart, you know the information. You don't know the distance between Earth and Mars when they're at their closest, but you do know the distance between the center of the sun and the center of Earth. You know the distance between the center of Mars and the center of the sun. So you can actually find that difference between them by just doing a quick little bit of subtraction. And then you can work the rest from there. So plug that into your actual equation, or you can solve it separately, then plug the numbers in, but I usually like to plug those numbers in the equation. So I have Newton's gravitational law to be your gravitational constant multiplied by the mass of Earth, multiplied by the mass of Mars, all divided by the difference between their radius of orbits squared. So make sure, again, here's the chart one more time, pick the appropriate values, right? The radius of orbit of Earth, radius of orbit of Mars, so note the numbers. Earth, I usually just remember it as 1.5 times 10 to the 11 meters, or 150 million meters from Earth to the sun. It's a rounded value, but typically that's good enough if you just need to know that. But obviously mathematically, you kind of want a slightly more accurate value. Mass of Earth is almost 6 times 10 to the 24. So those are numbers that will come up quite a bit. So if you have a rough idea of what those numbers should be, this stuff will get easy as you do some problems. Plug those numbers in, that's where they came from, right? So this is the constant, you'll remember that. This is the mass of the Earth. This is gonna be the mass of Mars. Mars is smaller, so its mass will be smaller. And then of course their radius is take the large number minus the smaller number.
All it's left to do is multiply the numerator going across and multiply the denominator going across. All right, and you should get some ugly numbers, and in the process, the kilograms from the gravitational constant should cancel out by the 2 kilogram values by multiplying by both their masses. And you should get some pretty big numbers here. Be comfortable with big numbers. A lot of your math is going to consist of scientific notation for the next little while. In fact, for the rest of the semester, you're going to be dealing with lots of really large numbers and lots of really small numbers. Right now, they're large, but so just get used to a lot of scientific notation. So multiply everything through. By the time you're at this point, you should have the units Newton meter square. Don't try to simplify this into anything else. After all, we want a Newton in the end because it's a force. Work your denominator through. So by the time you square it, you'll find that the meters should cancel out. You have a meter square in the bottom, meter square in the top. And again, the number will be kind of big. Do a quick little bit of division, and you'll find that you get a force that's somewhere around 4 times 10 to the 16 newtons. So it's a pretty large force, but after all, these are planetary bodies, so expect the numbers to be astronomical because you're dealing with space and celestial bodies and so on and so forth. Okay, I better stop this video. I'm going to ramble otherwise. So if you have any questions, just send me an email, work out this stuff. It's a little bit different than the stuff that you guys are probably used to. Mainly because most of the numbers aren't given to you, they're from that chart. So if I haven't driven that point home enough, make sure you keep that chart handy at all times. All right, have a good one.